something that I really like. You began some notes last night with that video, right? And in that video, you saw these steps right here, correct? Factor the denominator. Write the given problem as the number of factors determine how many fractions that need to be added together. If there is a linear factor, then the numerator is a constant, like we saw in our problem of the day. If there is a repeated factor, then you need to include the lesser powers of that factor. So x minus 1 and x minus 1 squared, for example. And then if there's a quadratic factor, then the numerator must be linear. All stuff from last night, correct? Okay. Questions about any of that before we continue? What we are going to do then is we're going to have to figure out what A and B and C and D or whatever our letters are. We have to figure out what they are using some algebra. So what I'm going to ask you to do, here's the next thing you need to write down, is I'm going to ask you to simplify by multiplying the LCD on both sides. Essentially, whatever your common denominator is, multiply everything by it. And what that's going to do for you is that's going to get rid of your fractions. My highlights got all off here. Okay. The next thing I'm going to have you do is solve for the constants, and I'm actually going to show you two different ways to do that. We're either going to substitute zeros in for our factors so that things cancel out and we can figure out what that constant is. Or I'm going to show you a method that I call compare coefficients, where we compare the x squareds, the x's, and the constants together to figure out our A, B, and C. Okay. And then, of course, once we solve, we're going to actually have to write our answer. Okay. The whole purpose of this is to decompose our fraction. Okay, we're breaking it up into multiple parts. Okay, so instead of one fraction, we're essentially making like an addition problem, right? I want to break this up into fractions added together. Okay, believe it or not, it is actually a useful thing. I'm actually going back in my Calculus BC class, and we are going to remember this method so that we can use it to help us with something in calculus. Okay, so I don't want you to think that this is meaningless. It's not. It actually is helpful in certain cases to have a fraction broken apart. Okay. Are you ready? Okay. How many of you really love doing algebra? Like not the graphing part, but like the solving for the x's and things like that. How many of you just really like algebra? Okay, this is your day. All right. Okay, so this was our problem of the day. Okay, x plus 8 over x squared plus 6x plus 8. And we factored the denominator to x plus 4 times x plus 2. And we broke this up. You know what, I'm going to rewrite it. Okay, we factored it. And then we broke it up to a over x plus 4 plus b over x plus 2. Is it going to show up? Ah, there it is. Okay. All right. At this point, I want you to multiply by the LCD. That just means multiply by the common denominator. Your common denominator is going to be whatever is right here. Okay? So in this case, we are going to multiply by x plus 4 times x plus 2. Whatever that original denominator is, multiply by it. Okay, in its factored form. Okay. All right, so what happens? When we take this LCD and we multiply it by this left side, what happens? We are only left with x plus 8 because the x plus 4's cancel and the x plus 2's cancel, right? Okay. What happens when we take this and we multiply to this fraction right here? Okay, our x plus 4's are going to cancel. Do you see that? Our x plus 4's are going to cancel, and we're going to be left with our numerator a times x plus 2. Then when we take this LCD times this last fraction, the x plus 2's are going to cancel, and we're left with the numerator times x plus 4. Our goal is now to solve for a and b. And like I said, I'm going to show you 2 different ways we're going to do that. The first way I'm going to show you is what's called, or what I call just plugging in zeros. Okay. We need to solve for a and b. We know that if we plug a value in for x, it should satisfy our equation, right? So what value could I plug into x to make this all disappear right here? Say louder. If I plug in negative 2 plus 2 is 0, and 0 times a is 0. So what we can do, if we say, all right, if x equals negative 2, then we can plug a negative 2 in for all of our x's. Okay, well, what does that leave us with? That leaves us with 6 equals 0 plus 2b. So what's b? Okay, turn to your neighbor. What is a different number for x that we could plug into to help us find a? Turn to your neighbor. Kaya, what do you and your neighbor think? Negative 4. If we plug negative 4 in for x, if we plug negative 4 in for x, this factor right here is 0, and 0 times b is 0. So we end up with 4 equals negative 2a, right? So a is negative 2. Okay, you are not finished. Yay, we've solved for a and b, but what do I actually want to see? Okay, well, I want to see some x's, right? Our whole purpose is to take this and write it as the sum of some fractions. So we need to go back and write it that way. So we wrote that x plus 8 over x squared plus 6x plus 8 was a over x plus 4 plus b over x plus 2. This right here is what I want to see. Go back to your original setup. A over x plus 4 plus b over x plus 2. And throw in what you solved for, a and b. That's the answer. That's it. But what happens sometimes is I get people so excited that they found A and B, they forget to actually write their answer, which is why I'm trying to make it a big deal right now. Questions, thoughts?
What if you like have like A over X plus 2? Does it matter?
Oh, that is an excellent question. What if you set it up as A over X plus 2 plus B over X plus 4? Okay, what's going to happen is your A's and B's would just be backwards of mine. And what would happen is you would still end up with 3 over X plus 2. And you would still end up with negative 2 over X plus 4. Your A's and B's would just be in different places than mine. Does that make sense? Yeah. You're still going to get to the same answer. Your work is just going to look a little bit different with your A's and B's. Okay? Very good question. Okay? All right. Go ahead and write this one down. And then what I'd like you to do is at your pod for the next 30 to 60 seconds, work on factoring that denominator. Just factor the denominator. That's all I need right now. Okay, our denominator. Emma Ralston, what does it factor to?
X times X plus 1 times X plus 1.
Okay, are you okay if I write it like that? Yeah. Okay, so we have X times X plus 1 times X plus 1, which I'm going to encourage you to write as X plus 1 squared. Okay, so how are we going to set up our fractions? First of all, how many fractions? Yes. Okay, how many fractions do we need, Edison? 3. We need 3 fractions. We have 3 factors, so we need 1, 2, 3. Here's the thing, though. Each of our denominators have to be different. Okay? So this one's easy. What's our first denominator? X. What should we put for the second one? I'm going to go in this order if that's okay. All right. I'm going to put X plus 1 here. I cannot put X plus 1 here. Otherwise, we'd be able to add these two together because they have the same denominator. Remember, if we have... Yes, I do. Oh, yeah, I can. Okay, sorry. So here we have X plus 1. When we have any factor to a power, we need to represent each of the powers. So here's X plus 1 to the first, and then we need X plus 1 to the second. Okay. Are these all linear? Is this a repeated linear factor? Then we're still going to treat it as linear, okay? Thank you. I know that if you were to multiply that out, it would be quadratic. I get that. But the factor itself is linear. It's just a repeated linear factor. So we're still going to treat it as such. Okay? Questions before we continue with that?
Why is there 2, like, Why do you have to set, like, keep it x? Why is it just x plus 1 and x plus 1?
Okay. So if they both had a denominator of x plus 1, they wouldn't really be two separate fractions because we'd be able to just add them together because they have the same denominator. So we have to have 3 unique denominators so that they can't be added together without doing some algebra to get them to common denominators. Does that make sense? Okay. All right. So at this point, we're going to multiply by our LCD. Okay. What's really nice about multiplying by our LCD is it's always going to cancel out your original denominator. So we have 5x squared plus 20x plus 6 on the left side. If we multiply by this to this first fraction, if we take our LCD and we multiply it by this first fraction, what will cancel out? The x's. So we're going to be left with a times x plus 1 squared. Kinley, what's going to cancel out if I multiply it to the second one? One of the x plus 1. So we're going to have b times x plus 1, because only one of them will cancel out. Okay? And then if we multiply this LCD to our last fraction, okay, Max, what's going to be left there?
Just the x.
Okay, so we have c times x, because the x plus 1 squares will cancel. Everyone okay with that? Okay, so let's think of some numbers that could help us solve for A, B, or C. Okay, I want to encourage you to look for things that make our factors 0. All right, so Mara, what's a number that would make one of these factors 0? Negative 1. Okay, negative 1 is going to make this factor right here 0. Do you agree? Okay. So now, are we capable of doing some mental math? Yeah. Okay, so I'm going to save us some pencil lead here. 5 times negative 1 squared is just positive 5. Minus 20 plus 6. Negative what? What's going to happen here? It's going to be 0, right? Negative 1 plus 1 squared is 0. Okay. B times negative 1 times 0, right? The whole point is to make that 0. Okay. So what we have is C times negative 1. C equals 9. Okay. Now, if you want to write out all of that work, you're more than welcome. But what I'm telling you is I feel that we've reached a point in our math career that we are capable of a little bit of mental math, and I'm fine with that. Okay? All right. What's another number we can plug in for x? I think you said 0. I'm not sure who that was. A fancy 0. Okay? We have the factor of x, so we can plug in 0 to make that go away. So over here, 5 times 0 squared plus 20 times 0 plus 6. We would have 6 on the left side. Here we would have a times 0 plus 1 squared. Okay. Plus b times 0 times 1 plus c times 0. Okay, A is 6. Well, shoot. We've plugged in all of our zeros for the factors, but we still didn't get B. Could we plug in C and A? Yes, we could plug in C and A. We know A is 6, and we know C is 9. And so then at that point, could we just plug in any random X value? I mean, we're picking strategic random X values here, right? Could we just do another one? What would be an easy number to plug in? 1 would be an easy number to plug in. If X equals 1, we would have 31, right? Okay. A times 2 squared plus, oh, we know A is 6 though. Okay, we know A is 6, 1 plus 1 squared, plus B times 1 plus 1, plus C times X. So what I've done, I've plugged in a 1 everywhere for X. I replaced A with 6 and C with 9. Now we can solve for B. If you have it for me, let me know. Everyone's just afraid to say their answer, huh? -1 is right. From the work that I did, at least on that. Okay, why did we have to do that? When we have that repeated linear factor, we have some repetition in our algebra. So when you have a repeated factor, you're going to have that trouble of you're going to be able to find a couple of them, but then that last one you're going to have to plug in a number if you do this method. Okay, so now at this point we know that, okay, our original problem, I'm just rewriting it. You don't necessarily need to. I'm just reminding you what we did. Okay, we set this up to be A over X plus B over X plus 1. Since B is negative, it's fine for you to write plus -1 over X plus 1. It's also fine for you to write -1 over X plus 1, because that would mean the same thing. Whoops, maybe I should actually replace A. What do you think? And then plus C over X plus 1, the quantity squared. Next, did you have a comment? You feel enlightened? Do you like this?
Yeah.
Okay. And you don't have to like it. It's okay if you don't. But questions before we move on to a different method. And I like this one too. This one is nice. If you have linear factors, I would really encourage you to use this method. Okay? What we're going to get an issue is when we get into our quadratic factors. And that's what I want to talk about next. Okay? Please use the zeroing out method when you have linear factors. When you don't have linear factors, then we have a problem. So go ahead and write this down. Okay? As a reminder, when you factor, you should always look for a GCF, okay? And I hope that's been ingrained in your brain, but here's your reminder if it's not, okay? Our denominator, we can factor out an x, and left over is x squared plus 4. factor x squared plus 4. If it was x squared minus 4, we'd be able to do it. But x squared plus 4, if you try to solve, like I'm going to come over here on the front board. If we set that equal to 0, we get imaginary numbers, right? Which means we're not going to be able to factor it with real numbers. Okay. So, we have a quadratic factor. Okay. So when we set up our partial fraction decomposition, I know that this is a cubic function in our denominator, but we only have 2 factors because that quadratic cannot be factored any further. So we're still going to set up 2 fractions, one for each of our factors. Since x is linear, we're going to put a constant at the top. But when we have a quadratic factor, I told you that you need a linear numerator. Basically, whatever the degree is, one less goes up top. And I had you set one of these up in the notes yesterday, correct? Okay, so this isn't news to you. Okay. How we're going to solve this, though, is going to have to be a little bit different. Okay, so let's go through our first motion. That's never going to change. We're going to need to multiply by the LCD. Okay, when we do that, of course, our very first denominator cancels. This fraction here, a over x, the x's cancel, and we're left with a times x squared plus 4. Here's where you need to be careful. The x squared plus 4's cancel. So the quantity bx plus c, I have to put it in parentheses, is being multiplied to x. You have to put that into parentheses because it's more than one term and it's all being multiplied by, in this case, x. Okay? Now, here's the issue. We could plug in 0 for x and be able to find a. But do we have a real number that we could plug in here to zero this out? Okay, we don't. So when you have a quadratic factor, it is not going to work to just plug in the 0 factor, the zeros of the factors, because we have some imaginary numbers that would zero that out. So when you have a quadratic factor, you are going to be forced to use the comparing coefficients method. So this is what I'm going to have you do. Okay? Do you see how I have 3x squared plus 4x plus 4 over here? Okay. On this right side, whatever it is should equal 3x squared plus 4x plus 4. Do you agree? We have an equation. What's on one side better equal the other side. Correct? So what I'm going to do is I'm going to go ahead and multiply all of this out. So I have a times x squared plus 4. And I have x times bx plus c. Okay. And then just for organizational purposes, I'm going to go ahead and rearrange everything. So since my left side is nice and organized by degree, I'm going to go ahead and rearrange so I have ax squared plus bx squared. I want my x squareds by each other. I'm going to rearrange so I have my cx and then plus 4a. Essentially, I just reordered everything so I can see where each of my terms were. Okay. So I call this method comparing coefficients, okay? If I have 3x squared plus 4x plus 4, I need 3x squared plus 4x plus 4 on the other side. So if I have 3x squared here, that also needs to be 3x squared. So I'm going to write a plus b should equal 3. When those two get added together, it should equal 3 because that's the coefficients of the x squared. Okay. For x. Over here I have cx. So that tells us that c equals 4. My constant is 4. Over here, my constant is 4a. So 4a equals 4. Okay. Now, I know that this isn't very intense, but this is why this section is in Chapter 7, because we have a system of equations here. Thank you. We have 3 equations with 3 unknowns. Now, how long is it going to take us to solve this one? Not very long. But if it was more intricate, we have the tools to solve it. Okay? This one's actually pretty nice. A is 1. And if a plus b is 3, then b is 2. All right, so we have it. So we're going to write our answer as a over x plus bx plus c over x squared plus 4. Oh, I keep doing that, don't I? Actually, got to write the value. Question. Let me come back up to here. Okay. This method that we just did comparing the coefficients, it will work for any of the problems that you do. My only warning to you is that you could get into a systems of equations that has maybe 3, 4, 5 variables. Okay, so in my opinion, if you have linear factors, stick with the zero out method. If you have quadratic factors, you have no option but to do the comparing coefficients. Okay, all right. I want you to think about what we just did. I want you to think about how you feel about it. And just give me a little feedback so I know where you stand as you walk out the door. You can circle more than one, but just let me know how you feel and why, or like which emoji and why you feel that way.